Welcome to the TCS at Jagiellonian seminar. Today our guest is Alex Scott from the University of Oxford. Alex is well known for his work in structural graph theory, his work on induced subgraphs, on high-boundedness. He is an invited speaker to this year's International Congress of Mathematics. And today he will tell us about induced subgraphs of large chromatic number.
Great, thank you very much. Thank you very much for the invitation. So it's my first time in Poland, and therefore my first time in Krakow as well. So it's great to be here, wonderful to meet people and talk with people. Okay, I should say that the title's a little bit of a joke, because we tried to think of a good title, and this made people laugh, so this is what we ended up with. So the work I'm going to be talking about is joint with this collection of people. So Antonio Girão, Freddie Illingworth, Emil Gawiarski, Michael Favory, James Han, and Yuri Tmitagama. They're all in Oxford, so Antonio and Freddie are postdocs, and Emil, Michael, Jane, and Yuri are PhD students. Okay, so this is some joint work from a month or two ago. Okay, so there've been lots of exciting things that happened with looking at chromatic number recently. So the last sort of few years, lots of different people have proved lots of really interesting results. But in some ways, there's lots of things that are still quite mysterious about chromatic number, and particularly graphs of large chromatic number. So questions like, what must they contain and what need they not contain? So the first question, okay, let me also say maybe it's what can you say about the structure of a graph with large chromatic number? So chromatic number at least 3, you can say something. You can say, okay, it has to have an odd cycle. Anything else, anything higher, it instantly gets much more difficult and kind of hard to pin down. Okay, so what's the first question you might ask? So you might ask, if G has large chromatic number, does it have to contain a triangle? So the first question when you first meet chromatic number, kind of sensible question to ask is, if G has large chi for chromatic number, must it contain a triangle? So must it contain a copy of K3? And of course, the answer is no. I mean, there were lots of constructions. It was, I think, first shown by Tut in the 1940s. There are nice constructions of Zykov and Michalski in the 1950s. And Polish also in the late 1950s showed that they're in fact graphs with both large chromatic number and large girth, so no short cycles at all. So that's one of the first applications of the probabilistic method. Okay, so that's very well known. Okay, here's another question. So, okay, right, we know you don't have to have triangles. Here's something else you could hope to do. Start with a graph with a very large chromatic number and then drop to some induced subgraph. By the way, everything in this talk is going to be about induced subgraphs. So unless I explicitly say, almost everything, unless I explicitly say subgraph, I mean, and make a point of saying, and not induced, I mean induced always. Okay, so here's one thing you might hope to do. Start with a graph of huge chromatic number, kind of big, complicated, messy, and maybe drop to an induced subgraph that's nice in some way, so, or a little bit nicer than you started out with. Okay, so we know there are graphs with large chromatic number and no triangle. Maybe you can drop to maybe you can drop to a nice induced subgraph. Maybe, okay, well, you can't immediately hope for triangle free because you might just start out with a clique. You might be a giant clique. Okay, well, that's another nice outcome. Big clique has large chromatic number. Great. That's nice and simple. Okay, but if you don't have a big clique, maybe you could ask for a nice triangle free graph with large chromatic number. Okay, so the general question is if G large pi and G subgraph nice. Okay, and has large pi. Okay, and as I said, so large clique must be one outcome. Okay, so that's sort of just simply unavoidable. Okay, question that Louis Esperet asked. So he said, so if G has large pi, no complete subgraph of fixed size, must it have an induced subgraph that's triangle free and has large chromatic number? Subgraph, induced subgraph. Large pi. In other words, by dropping to induced subgraph, if we don't have a large clique to begin with, can we at least get rid of any kind of medium-sized cliques? Okay. So I'd say that, I mean, Louis asked sort of a couple of really nice questions. There's another one about polynomial chi-boundedness that's also, so I think this has been answered, not by us, and the other question has been answered as well. So there's a lovely question about polynomial chi-boundedness that people have thought about quite a lot. This one's also really nice. And Louis seems to have this ability to ask questions to which the answer is obviously no. And then you look at it and try and do it, and it's actually not so obvious at all when you come down to it. So this sort of, I think it's slightly unfair to say after the question's been answered, but I look at this and think, shouldn't the answer be no? But you know, it's no good unless you can actually come up with a proof. Okay, so it was a kind of real teaser of a question, and would have been, yeah, the answer is very interesting either way. So it was answered. Comp. No. So they gave a very nice construction, which I will come back to and talk about the history of in a second. And then there's a I should actually also say I'm doing things slightly well. There's an English phrase, kind of bringing coals to Newcastle, and I'm doing that a bit here because it means I probably all know what it means, but it means taking something somewhere where you already have lots of it. And I will talk about results of several people in the audience here, so I hope I will represent you correctly. But please interrupt and tell me if I'm saying anything wrong. Yeah, so Bransky. So they proved a more general thing. So replacing K3 free by larger cliques. Okay, so replace. And they did some more stuff, which I'll come back to in a bit. Okay, so right. But I'd like to say what we did first, and then we'll come back to everything. Okay, so we'll prove what we did is we proved something rather more general. actually, before I say that, let me just emphasize, these are really nice results. These are really not at all obvious. So one of the problems with graphs of large chromatic number, I said there's lots of constructions of triangle-free graphs for large chromatic number. There's a bunch of constructions of graphs with large girth and large chromatic number, but in some sense we're quite poor in constructions. So we're not good yet at kind of finding constructions that avoid substructures or really capture a lot of things that are there. So it's sort of this big kind of foggy area that we're still slowly working our way into as a community, but there's a lot still to be done. So it's sort of these things are not obvious and really weren't obvious at all kind of 3 months ago. Okay, so let me see what we can do. So for every graph F, at least one edge, trivial case. Yeah. So for every graph F, there's constant such that the graphs arbitrarily large, so graph H, arbitrarily large chromatic number, such that so two things, they have the same clique number, omega, writing omega for the size of the largest complete subgraph. So they have the same clique number as F. And secondly, every induced subgraph is contains an induced copy of F. So any subgraph, induced subgraph with large chromatic number, bang, you get a copy of F. Okay. So one way to think about this is as a strong type of Ramsey property. So there are these things called Ramsey classes that were studied by Sauer and Nestor and other people. And you might say, okay, I'm interested in copies of F. I've got my great big graph. I want the property, whenever I partition the vertices into a small number of classes, one of them should contain an induced copy of F. Okay, so actually those aren't very hard to construct, but once you start excluding more than one graph, it gets quite thorny. Okay, this is the slightly different statement that whenever I take a reasonably large piece of the graph, size measured by chromatic number here, then somewhere in there is a copy of F. So that's the property that we're after. Okay. Okay, let me say the second theorem as well. So that contains cycle. So there's an odd girth version of the theorem. So the odd girth is the length of the shortest odd cycle in the graph. Okay, so there's a constant C prime F or CF prime. Graphs arbitrarily large prime. Okay, so we have the same odd girth. So in other words, H might contain a huge bipartite subgraph. We're not worried about even cycles. We're worried about just the shortest odd cycle. And then the same property again. So same again with So the same property that if you take any induced subgraph with large chromatic number, then bang, you get a induced copy of the thing you're interested in. Okay.
And still the cliques number are the same.
Yes. Good. Okay. So both these two earlier results sit on the Zykov graph, although I believe there's a new version of this that uses something else. But let me start by talking about the Zykov graph, and then I'll be in a position to talk about the history a bit better. So. Actually, no, wait, let me do it the other way around. So I should say both these previous results build on a really nice idea from a paper of Kirstead and Trotter, which was interested in actually the Jaffa-Sumner conjecture for directed graphs. And that has a really nice counterexample. And history is essentially that this Carbonneau, Moore, and Sperkel paper notices that it's a clever thing. They noticed that the really nice Kirstead-Trotter construction can be essentially, if you forget the orientation in some sense, you obtain a graph that proves the first theorem. So it's essentially it's a slight tweak of their construction. And then the second paper sort of simplifies and generalizes it. The thing I'm not going to talk about there with the second paper, so I'm going to give this construction. The thing in the second paper I'm not going to talk about, there's lots of clever stuff actually bounding the chromatic number. So and that requires a couple of additional ideas is very much non-trivial. Okay, so but I just want to take the basic construction, and then I'll talk about how it's modified, how we modify it. So you need some extra ideas to get these results. Okay, so let's start with the basic Zykov graph. So yeah, this is going to be built on the Zykov graph, this first result. We're going to have to use something else as a base graph for the second result. Okay, so okay, so Zykov graph ZN. Okay, so here's a construction of a triangle-free graph with large chromatic number, and it's very simple. So Z1 is just a single vertex, and as I'm aware most of you know already, Zn plus 1, you just take n plus 1 copies of Zn, and then you add a new vertex with one neighbor in each in all possible ways. Okay, so clearly that doesn't contain any triangles because these vertices lie on different copies of Zn. Okay, so there's another one joined to the next choice and so forth. So lots of new, it blows up exponentially in terms of number of vertices to each step. And we're going to orient it as well. So we'll just orient all the edges towards later parts of the construction. Okay, so really we're taking oriented graph. Okay, and it's easy to check. You get two properties, so chromatic number of is equal to n, and secondly, all x and y, if you take any two vertices, and this is a really useful property, there's at most one directed path from x to y. So there's at most one directed path from x to y. Okay, and if you, I mean, it is easy to check. You just look at the inductive step in the construction. So if x and y both lie in some copy of Zn, it's immediate. If they lie in different copies of Zn, there are no paths between them. And if y is one of these vertices, well, there's only one way in, and then you're done by induction. Okay, so easily checked. Again, and it's acyclic as well. It kind of clearly goes earlier generations to later generations. Okay. Note that it's acyclic as well. And these are the only properties we're going to use. Okay, so we're not actually going to use anything about the structure of the graph itself. Okay. Right, so let's start with the earlier constructions. So first one of the early constructions. So start with Zn. I'll just write Z because I'm not going to, and N is just going to be very large. So I'll just take some late generation of the Z graph. Okay, and oh yeah, okay, I didn't know. Well, it's also triangle free. It's worth noting down. Okay, fix a prime P. And just do the following. So for any x and y, all x, y. So join x and y if there's a path from x to y of non-zero length mod P. So if this attractive path y non-zero. Okay. So I should say they've announced a kind of more general version of this that gets rid of the constraints on primality, but this is the first version. Okay. Right. So two things to check, and maybe I'll sort of quickly mention the arguments because they're useful later as well. So firstly, clique number of I'll write H for the result after we've added all these edges. Okay, so I hope the construction is clear. So whenever you have a path, a directed path between X and Y, so you forget the original graph. Now add an edge whenever the length of the path between 2 points is not congruent to 0 mod P. Okay.
So you do have initial edges as well.
Yeah, but you have them as edges of length 1 mod P rather than not. You forget the directions as well. Really. Yeah. Okay. So first, peak number is P. So well, it's at least P because if you just take a path in the original graph of length P, or with P vertices, sorry, length P minus 1, then you get a clique on that. So all the lengths are less than P. On the other hand, if you have a clique, so here we are, well, there's some ordering on the vertices because it's an acyclic graph and you have to get from any vertex to any other with a directed path. So there's actually a path that goes through all of them. And we just say, okay, starting from here, I look at the lengths, mod P. And if I've got P plus 1 vertices here, 2 of them must have the same length. And so the path between them has length multiple of P. So there's a non-edge in there somewhere. Okay, so that's immediate. And then sort of the important bit, so induced subgraphs with omega smaller than p have bounded chromatic number. Okay. Now I believe you had a seminar on a closely related topic last week, so in some sense you've seen this. I mean, those of you that didn't produce the argument yourselves already have seen the argument. But I'll say very quickly, you split by the length of the edge that you've added. So for each edge, it came from a path of some length mod p. So let's look at just the edges of length, let's say I mod p. There's p different choices. Okay, so suppose you have a long sequence, and here we are. This is a path of length I, path of length I, path of length I. So, right, space, let me draw here. Okay, so suppose there's a long path, and here we go. Each of these came from a path of length I mod p. Okay, so, right. Well, p is prime, and I isn't. So I is less than p. So these multiple, I mean, the total length from the beginning, you're running through just the residue classes in some order. So it's I, 2i, 3i, 4i, and so on. And so you can't have a path of length p, otherwise, well, you can't have a path with p vertices, otherwise you've got a clique on it. Okay, so all these distances, if we go 1 up to p here, all these distances will be non-zero on p. There'll be I multiplied by something smaller than p. Okay, so you would get a clique. What does that tell you? There's no, if you look at the edges corresponding to paths of length I, there's no path of those of length, so of length p. Okay, and then there's an easy argument that says that means that you have bounded chromatic number. Just for every vertex, look at the longest path starting there in that color. So for each distance, modulo p, the subgraph with those edges has bounded chromatic number, and now chromatic number of the unions at most of the product of chromatic numbers. Okay, so that gives a sort of very crude bound, sort of something like p to the order p. There are much better bounds. So yeah, so Briansky Davis and Bogdan have produced something much stronger. Okay. So this sort of second part is going to sit through the other two, through the two theorems I'm going to talk about, and the arguments can be essentially the same. That's why I'm going through it. Okay. So the difficult thing is going to be making sure that the graph we want actually appears in a induced subgraph. So we need some mechanism to make it pop up. Okay. So right. Yeah, other things to say. So, yeah, so the Girth and Trotter construction is essentially the p equals 2 case of this. And then the Carbonaro-Homp, Moore and Sperkel construction. So essentially, it's the p equals 3 case of this. And then the more recent construction is the general p case. Okay, so that's sort of so it's actually been a nice flow of kind of people handing off to, groups handing off to other groups. But it starts with the Girth and Trotter construction. Okay. Okay, good. Right. So what do we do? So this is going to be a proof of the first theorem. So we start with Z or some Zn. Okay, so remember that it's triangle free and for all x and y, there exists at most one x to y. Okay. So some graph F that we're after. Right. Let's start by choosing a prime P. And for something of order, some constant times number of vertices in F cubed will be enough. Let's take a 3 set. Okay, so we'll take some integers between 1 and P, and I want them to be a B3 set, which means if I take solve, any way to solve x1 plus x2 plus x3 is equal to y1 plus y2 plus y3 is if I've got the same sum on both sides. Three equals y1, y2, y3. And I'm writing that slightly informally because I mean that with multiplicity as well. So if I've got x plus x plus x on the left, I have y plus y plus y on the right. Okay, so I'll just say take multiplicity. Okay, so the only way of getting three things, so a sum with three elements to be equal to another sum with three elements is just to have the same three numbers just rearranged. Okay. Right. So these things have been, so B2, B3, BK sets have been quite well studied. And you can take S to be, so S to be a sort of some constant times e to the third. And it's sort of easy probabilistic construction if you're not bothered about how large the constant is. Right, and in particular, those these largest set. So this is what's pushing up P. We need it to be big enough to fit in the B3 set. Okay. Identify the vertices of F. Elements. Yes. Okay, so that's the idea. So for instance, if our graph looks like that, I have S1, S2, S3, S4. So each vertex gets a number in our B3 set. And now do the same construction, but we only join vertices if the distance between them is one of these distances, mod P. Okay, so starting with Z, join X and Y, distance from X to Y. So if there exists a X to Y path of length Sj minus Si P some edge J in F. Okay, and just for keeping signs tidied up, I'll assume everything, I could order everything from left to right. So I'll take it here, I'll assume that S1 is less than S2 is less than S3 is less than S4. And so the distances I get, so for instance, this edge crops up at distance S4 minus S2 mod P. Okay, so we throw in an equivalence class of edges. Okay, let me make kind of a little technical adjustment. So that's the idea. Let's also keep the original graph. Just forgetting the orientation. Just ensures that the chromatic number is nice and large. And I'll do that P over 6, just bump into the top. I don't want to worry about going over from past P plus 1 and bumping into myself. And what else? Okay. And we can assume also that everything in S is a multiple of 3. So, okay. Don't worry about those just little technical things to make everything tie up correctly. So this is the key idea. Okay. Right. So that's construction. Okay. So what's tricky here? So actually showing the peak number has gone up. For this construction, this is the main thing that you have to work with it for. So okay, so let's prove that the clique number of H is the same as the clique. Is the construction clear? Yeah. Okay, please interrupt with questions.
Can I just make a 10-second wrap up, just because I'm about to lose the flow. So F is an abstract graph, but you map the vertices of F onto this S, which is a B3 set, yes? So yes. The edges of F so far play no role. You map the vertices on top of on S.
Yeah.
And then you Then you put labels on
right. So I've given each vertex of F. So here F is the 3-edge path.
Yes, yes.
Drawn in this order. Each vertex gets a number.
Yes.
And the numbers are nicely spread out.
Yes.
And this is sort of technical B3 condition.
Yes.
Numbers are nicely spread out. And for each edge, so that's a length. So this edge has length S4 minus S2. So now in the construction, I'll put in an edge whenever the path from X to Y has one of these lengths, mod P.
I see.
Okay, so previously it was whenever the length was non-zero mod P. Now it's whenever the length is one of these very specially chosen differences mod P. Okay, so it's going to be a reasonably sparse graph because we're working mod P and there's only at most P to the third vertices. Okay. Yeah, again, these exact numbers don't matter too much for understanding what's going on. You just need to know that P is nice and big, and we've chosen F. We've chosen these values at the vertices nice and spread out, and it's to avoid certain dependencies happening. Okay, and it's going to crop up exactly in this bit. So proving that the clique number hasn't come up. Okay. Any other questions before I leap into more detail? Okay. So what we want to check is that the clique number of the graphs we construct. So I should say that chromatic number is large because we've kept the edges from the original Z. Okay. Now I want to check that there's no big clique. So I said it but didn't write it down. So with slightly informal because I'm working mod P, but anyway, all multiples of 3. So I want S to be, the elements of S to be multiples of 3 that are smaller than P over 6. Okay, again, it comes for free, just make P a bit bigger if you want. So and by making the multiples of 3, I'm not going to get any triangles or involving edges from the underlying graph F. So all lengths are either exactly 1, not mod P, just exactly 1. So coming from the original Z-cop graph, or multiples of 3. So if I'm going to get a triangle, it's going to involve 3 paths of length multiple of 3. Okay, so let me convince you that the graph we create has length, has the same clique number as F did. Okay, so suppose as a triangle, let's see what happens with the triangle. Okay, so we've got 3 vertices in H. And the first one came from some edge in here, y1 minus x1. So this is a path of length y1 minus x1 mod p. And then similarly here and here, there must be some path that's of, say, length y2 minus x2 mod p. And there's some path here, which is just a concatenation of these other two, because there's only one path between any 2 vertices of length y3 minus x3 mod p. Okay. So we have y1 minus x1 plus y2 minus x2 equal to y3 minus x3. Okay, and this is why I wanted to avoid kind of going around all the way around the clock. So I made everything smaller than p over 6 for convenience. So this actually is a sum, not just mod p, but just in the integers. Okay. That implies that the triple x1, x2, x3 is equal to the triple y1, y2, y3 in some order. Okay. Okay. Right. So let's see, x1, x2, x3, y1, y2, y3. So we've got y1 minus x1, y2 minus x2, y3 minus x3. So there's some correspondence between them. So it could be that x1 is the same as y2. So these are different because lengths are non-zero. Or it could be x1 is the same as y3, and then you can sort of fill out the matching. So let's see here, x3 has to go to y1, x2 to y3, and here x2 has to go to y1. Okay, so you get that. So let's just look at this one, and the other one is the same turned around.
And everybody's, you start not with that triple, you start with y1, y2, x3 is the same as x1, x2, y3.
Ah, damn. First time I've sworn on the internet. Okay, yeah, okay, up to sign. Yeah, okay. Let me not get lost in the details. This I just say this is easy. Yes.
Just slow. That's
Slightly inelegant. Yes. Okay. Yeah. Thank you, Tom. Okay, so I swapped x3 and y3.
No,
it's cool.
Ah, yeah, sorry, this is right. Okay. Right. So okay, so let's see what does this give us? So this means our 3 lengths are x1 is the same as y2. So our lengths were y1 minus y2, and then y2 minus x2. So that's going to be y2 minus y2 minus y3. And the third one was x3 minus y3. That's going to be y1 minus y3. So what does that tell us? So we've got y3, y2, y1, and this corresponds to a triangle in F, because y1 minus y2, y2 minus y3, good, it would work, y1 minus y3. So that corresponds to, okay, and the other one works just the same if you get the labeling right. Okay, so triangles in this graph correspond to triangles in F. More generally, if I take a larger complete graph, then so each triangle here corresponds to a triangle in F, and you can check the triangles have to glue together in the obvious way. So you get, basically you either get y1, y2, y3 in that order or the other order, and it has to be consistent, and it glues together into a bigger clique. So I won't go through the details, they're not hard. Good. Right, that controls the chromatic number, and that's the point of introducing these B3 sets in order to get this control. The other bit was applies with chi. So that's actually easy. It's exactly the same argument. So it's just we're not introducing anything new there. Maybe a quick side comment. We get quite large bounds here. So it is p to some power of p. So exponential in some power of p. It's not obvious that it's so easy to reduce them, even with the ideas of Briansky, Davis, and Walksack, because we don't have a complete graph. We've got some sort of sparse graph that we're putting in. At least to us, it's not obvious how to improve our bounds to something sensible. Okay. Good. Let me talk about the odd girth result. Okay, so okay, so we start with a oriented graph. So what we want. Cyclic large chromatic number. Again, this property so for any pair of vertices, there's at most one path between them. And the new property here is that every cycle underlying graph has G direction. By which I mean, if you take a cycling underlying graph and look at what orientation you get in Y, then as you walk around the cycle, you change orientation at least G times. Okay. For brevity, I'll refer to this as write this as COD for change of direction. Okay, so let me sketch a construction of these.
So Girth was the shortest odd cycle.
Yes, yeah. So I'm not going to mention odd girth yet. So this is entirely about changes of direction. Okay, so the construction is built in the construction of natural Gödel. And it's a piece of a construction. You're laughing at the accents. Okay. I apologize to the entire world for my accenting.
Avoid the rule is turning over.
There we are. Do it properly. Okay. Right. So it's I think a very beautiful construction of Nash and Randall. So it's a graph with large girth, so large girth, chromatic number n, and is n partite as well. So this is let me show you the construction. So it's very, very clever, and I think it's nice to see it. So let's start with E0, and it's just going to be, E0 is going to be very simply n sets, and then for each pair of sets, we'll put one edge between them, which have slightly fewer. There we are. So go. There we are. It's disjoint edges. Vertex disjoint edges. Every pair of sets has one edge. Okay. And then we're going to go through just a sequence of rounds processing this. This is going to be called B0. Okay, and the thing we're going to add actually is we're just going to orient everything from left to right. So let me just note this does have the change of direction property trivially, because there are no cycles. Good. Okay. So choose a hypergraph with large girth and chromatic number. Okay, so here we are. So in there's lots of edges. It's got large girth. It's got large chromatic number. How big are the edges? It's going to be as big as this first class of B0. Okay, and I'm just going to take a copy of B0 for each of these edges and glue it on. Okay, so B0 is going to be n partite. We're processing the first class at the moment, and we're going to go through then the second class and the third class and so on. So this is going to be n steps to this. Okay, and these copies of B0 are disjoint other than just in that first class. Okay, and I'll call the result B1. Okay, so it's a great big n-partite graph. So this hypergraph construction means it's blown up a lot. Okay, how am I going to get B2? So I'll do the same thing again. There's a bit less. So again, it's a hypergraph with large girth and large chromatic number, and the size of the edges is the size of the second class of B1. Now we do the same thing again. We glue copies of B1, and the only place they overlap is in this second class. So they glue onto whatever the edge is in class 2, and otherwise they are disjoint. Okay, so we get lots of copies of B1, and we're going to call the result B2, and so on until we get to the last class. In the last class, I think it may be helpful just to for a hint of a picture. Here we are. We've got some absolutely staggeringly huge graph by this point, and we're gluing copies of the n-1 onto, again, a graph of large girth and large chromatic number. Okay, and every stage we just orient everything from left to right. Okay, so I need to convince you of two things. I need to convince you that the result has large chromatic number at least n, and I need to convince you that it has a change of direction property. Okay, so the chromatic number at least n. Let's consider a coloring of Bn. Okay, and now it's just beautiful because you look at this last class. Okay, it's a hypergraph with large girth and large chromatic number, so it has some edge that's monochromatic. Okay, so that edge came from a copy of Bn minus 1. So let's go back to, here we are, Bn minus 1. So I'm going to ignore the last vertex class for a second. So what was Bn minus 1? We glued lots of copies of Bn minus 2 onto a hypergraph with large girth, large chromatic number. Okay, and then they came out like this. Okay, well, this is a graph, hypergraph of large girth and large chromatic number. One of the edges
So this shaded area in the last picture
yeah.
is the union of everything you have on the right in the top picture, right?
I'm taking this whole.
Yes, and then
yeah.
on the last class you had the same color.
Yes.
And so they all there have the same color already when you draw it.
Yes.
So this
okay.
is the union.
Yeah. So let me say it more precisely because I think I forgot to say. So let's consider. I want to show this has chromatic number n. Let's consider a coloring with at most n-1 colors. Okay. So some edge in here is monochromatic. Some hyper edge in here is monochromatic. Here we are. Here's a monochromatic edge. We have a copy of Bn minus 1. Right. I'll draw that copy of Bn minus 1 up here. So this shaded edge is now that. But I'm going to look to the left now. And okay, this copy of Bn minus 1, all these edges are vertices and these edges are colored. Some edge must be monochromatic. Okay. So hypergraph, large girth, and large chromatic number. Let's say that edge is monochromatic. Now roll it back. Okay, so that came from some copy of Bn minus 2. This copy of Bn minus 2 has that class monochromatic, that class monochromatic. Okay. Carry on rolling it back, all the way back down to, here we are, copies of B0. Okay, when we get to this point, all classes are monochromatic except for the leftmost. Okay, this has large girth and large chromatic number, so one of the edges is monochromatic. One of the hyper edges is monochromatic. Okay, take that copy of B0. Where did I put it? Here we are. Now in this copy of B0, that's monochromatic, that's monochromatic, that's monochromatic, and that's monochromatic. But there's an edge between every pair of classes, so those colors must all be different. So we must have at least 8 colors. It's a very kind of pretty, very nice icon. And it can be used for lots of other things as well. So it's a sort of special case of something. Okay. Large chromatic number, why does it have the change of direction property? So we just argue by induction going the other way. So trivial here. Let's go here. Okay, what could a cycle in here look like? Okay, so it's going to be, well, it's going to have to be a sequence of excursions. So either, I'll look at a cycle, either it's contained in some, entirely contained in some B0, okay, in which case by induction we have the change of direction property, or it starts here, wanders off in some copy and then comes back. And then, okay, well, it has to go to another copy, so out it goes and back again. So it goes from a vertex in some edge to another vertex in some edge, and then a vertex in that new edge, a vertex there to a vertex in some other edge, and so on. Since this graph has since this hypergraph has large girth, we have to do this a large number of times. Okay, we can't close it up quickly. And inside each excursion, either you go right and then left, or, well, you can't go left here, but by the next time you can, or you go left and then right. But either way, there's a change of direction somewhere in the middle. Okay, so we get a large number of changes of direction. Okay, and then that just follows by induction. Okay, so it's the same rolling all the way through. Yeah.
So here by larger in hypergraph, you in particular mean that each two hyper edges intersect at one vertex.
Yes, yeah. So I didn't define girth, but So that's what I mean by a cycle. So this sort of loose version of cycle. But in particular, that is a very short cycle. Absolutely. Yes, absolutely. So no two edges meet in more than one vertex, and then and what that means, if you go out and then back here, unless you, well, you know, if you're going to go into another copy of one of the B's, then it's going to be glued to a different edge. So you'll move to a new edge each time. Is the point. Okay. Does that answer the question? Good. Okay, so we have the change of direction property. We have the large chromatic number. Okay, let me get to the construction. Start with y, some y with n large. So some again. Large n. Okay. It's B, and now. So rather than a B3 set, we bump the numbers up, BH. So H is going to be at least as large as the girth. So just think of it as something large enough. But essentially, it's the girth. BH hat S. Size. Okay, what does a BH set mean? So all sums of okay, so previously we had a B3 set that said all sums of size 3, or equivalently all sums of size at most 3 are distinct. This is now a BH set. Okay, and then the same construction. So identify of S. So we put in all edges of length, well, Sj minus Si whenever Ij is an edge of F. Okay, so it's exactly the same. Through this picture before, so S1, S2, S3, S4. So we'll put in edges of length. S3 minus S1 mod P, S4 minus S2 mod P, and S2 minus S1 mod P in this case. So it's exactly the same construction, in other words. Okay. Right. Well, I'm starting to run long, so let me just very briefly sketch what the point is. So the main point is going to be to show that in this construction, we don't get a short, odd cycle. So the fact that chromatic number is large, oh yeah, we do the same little tweaking as before. So we keep the underlying graph. We make sure everything's a multiple of 3 or whatever we want. I guess maybe we want some constant. And we make sure that everything is a most P over some reasonable constant. Okay, so whatever we need to make everything, to avoid little technicalities. Okay, so chromatic number is large. If you have large chromatic number, then you have an induced copy of F. Argument is exactly the same as before, so exactly the same as other people have used. So the main thing is showing that we don't get short cycles. Okay, so let's think about how to do that. Okay, so suppose short cycle. Okay. Well, each edge in the cycle corresponds to a walk, so it corresponds to a directed path in the graph. But it's a little bit more complicated than before, because previously we were mostly avoiding cliques, and so all the vertices ended neatly lined up. But now we could have some cycle that sort of goes up and then down, and then maybe up, and up again, and then down. Okay, so things that are slightly harder to avoid, so we have to just work a bit more to show they're not there. So this would be, I'll draw some suggestive vertices, there we are. This would be a 5 cycle. Right, so suppose we get an odd cycle. Well, this corresponds to a walk in the underlying graph. So here we go up here, and then down here, these edges oriented backwards, and then up here, and then down there. Okay, so this in Y walk. Y. Okay, so W traces out some subgraph, and we'll look at what type of subgraph it is. And there's going to be 2 cases: either it's got a cycle or it doesn't. So firstly, W contains a cycle. I'll just quickly gesture out, so I'm nearly done. A quick comment at the end. So firstly, what happens if W contains a cycle? Well, let's drop to a minimal subwalk that contains a cycle. Okay, so take a shortest segment of W that does trace out a cycle. So what does it trace out in total? There's some cycle in the graph, and then maybe there's some bits hanging off it, but that's all that the walk does. And okay, well, the walk comes in, I didn't say short, so short whole cycle, let's say length at most K. So the walk comes in at most K segments, all in one direction. So between each 2 vertices, it's a directed path. So what happens is maybe we start up here, but we walk a little bit along the cycle. It's a good time for colour. Walk a bit around the cycle. Maybe we end up off the cycle. Okay, that portion of the cycle is directed that way. Then we come back and maybe wander around a bit more, or maybe we work our way back and wander around that way a bit. But each time, what we see, the new bit we see is just some interval on the cycle. So it divides the cycle up into at most K pieces.
It does have to be contiguous, like maybe the interval you see is disjoint with the previous, maybe you enter somewhere on the side, yeah? So you leave the cycle and then you enter somewhere.
No, we're taking them. If we come back in again, then we've completed a cycle. Yeah. So it's the smallest subwalk that creates a cycle. Good. Yeah, and also if it comes back up, if it comes back through here and adds a bit more there, it has to be consistent with what it's just gone through. So. Okay, so it kind of traces out the whole cycle, breaks up into at most K segments, each of them are oriented one way or the other, but now we have a cycle with at most K changes of direction. Okay, so this is the point of the changes of direction, is because these are great big long paths rather than just individual edges in the underlying, in the graph in which everything is sitting. Okay, and I'll say the second possibility is that there's no cycle. So you sort of trace out some tree, and then you note that number of up steps, number of down steps. And I'll just say there's an argument a little bit like the one before to extract an odd cycle out of it. So I'll skip that argument. It's not hard, but just for the sake of time. But that's where we use the BH set property. So we've got each portion that we walk has length yi minus xi sum I. The number one's up, some numbers down. So that says the y's and the x's sum to the same thing, modulo which you call X and which you call Y, as Tom picked up earlier. So you get the same set of things up and down, and once you do the rearrangement, you find you end up with a short odd cycle in the graph. So you get a contradiction that way. Okay, I will stop that. Oh, no, wait, I'm not going to stop there. I'm going to mention one more thing and a conjecture, and I'm done. So,
excuse me,
yeah.
so like in the second case, you are using the fact that it is an odd cycle, right?
Yes. Yeah, I mean, you do get even cycles because you respond up and down, but yeah. So you get the x's, and these jumps are all of form yi minus xi. Okay, so each one corresponds to a jump between two x's, and the BH property ensures that has to happen. And then you take okay, well, because you have the same number, I mean, because you're passing up and down, this ends up as an Eulerian graph, and it has an odd number of edges, so there's an odd cycle. So here we are, there's the shortest odd cycle, and that gives you a contradiction. Okay, because it's not there in the graph. Good, let me mention two generalizations. So, well, not generalizations, two results using the same ideas. So, what you can do for graphs, you can do hypergraphs. It's not quite so clear what to say about cliques. It's not so interesting, maybe, to talk about cliques, but you can get the same threshold property that as soon as you have some subgraph with large chromatic number, you get an induced copy of your hypergraph H, and also for tournaments. So again, there's the same machinery gives you something similar for tournaments. So for every tournament T, there are tournaments with arbitrarily large chromatic number. So for every tournament T is a constant C, and tournaments of arbitrarily large chromatic number, so that every sub-tournament with chromatic number at least C contains a induced copy of the tournament you're interested in. Chromatic number of a tournament is a nice, well-defined thing. It's just how many pieces you need to have if you want to cut it into transitive sub-tournaments. So as a tournament of chromatic number two. Okay. So I won't talk about those followed by similar types of argument. Here's one thing that would be very nice to do, and we have no idea how to do. So for every f containing a cycle, take the odd Girth result and try to cross out the word odd. So vector, there's a constant CF. And graphs of arbitrarily large say Girth. So just replacing odd Girth with Girth, such that same conclusion. So such that we use subgraph these CF so I have to say I believe this has been conjectured in some form as well by Bransky, Davis, and Bogchak. Is that right? Do you conjecture this in some version? It will need some kind of really different idea because these constructions where you just do put in edges according to whatever your base graph. Constructions where you put in edges just according to the length of the path mod P. So whenever you have something like this, you can get great big complete bipartite graphs. So just not clear how to avoid this. Or I mean, if you take some long path that has several edges going out and several edges coming in, then all of these, if the path length is right, all of these are adjacent to all of those, you get a big bipartite graph. So you really, it needs something new, and it looks like it might be quite difficult, but it would be very nice to prove. Okay, I will stop there. I'm going over my time, so thank you.